We've got very abstract pattern recognition that even when most of the data's missing, we still extrapolate to common things, and we do it very accurately most of the time. So we were doing a lot of research to look at how could we build something that when the logo was very distorted or slightly obscured because it was from the side view of a player or something, that you could still say, oh, that's the Coca-Cola logo, or that's the McDonald's logo, or whatever it turned out to be, or even more complicated ones that you could accurately detect that, because as a human watcher, you'd be influenced by that vision. And it was a very difficult problem because a lot of the way that these models had been trained back then was very much sort of repetition of thousands of labelled images that were all very clean and very obvious. And starting to look at, well, what happens when it's occluded and what happens when it's distorted makes for a slightly different problem. So that's when I started looking at some of the research that had been done in audio to solve a vision problem. Because if you're thinking of trying to detect what people are saying, I mean, it's fine. In this sort of environment, it's nice and clean. But in a crowded room, you've got multiple conversations, you've got other background noise going on. So the ML models that were looking at audio had to clean all of that noise. So applying the same sort of models and techniques to vision gave a much better result. And that's one of the things that I've always tried to do, is look at the problem and then try and find similar things from completely separate fields that we can use in order to solve the problem at hand, rather than just looking at a very narrow field of research.